Awesome. Thank you so much. Let's see. I'm Bogdan. I'm one of the co-founders and the CTO of Datology. I'm here with Fan.
Hello, I'm Fan. I'm the founding member of technical staff at Datology.
Awesome. And today we're going to talk about the engineering lessons from scaling synthetic data for trillion token scale pre-training. First and foremost, who are we? We're Datology. We're basically a data curation product. Customers come to us, either startups or large enterprises, to identify the best subsets of their data in order for them to train, pre-train, and mid-train their models, right? So in general, they have a bunch of data. They need help identifying the best subset of them, filtering, deduping, transforming, augmenting, generating synthetic data, all of those things so that they can get the best data sets possible. This product gets deployed on the customer side, so it sits within their cloud environment, and then they kind of point it at their data, and what we do is we ingest, filter, transform, augment, et cetera. And then we give them a data set back. And what they see kind of three things. They see that they can train these models much, much faster than before, 10 to 20 times faster. They can get models that are just of higher performance overall, somewhere between 8 to 12 percentage points on top of their existing baselines. And they can train models that are kind of 1 to 2 sizes lower in terms of parameters to the same or even better performance than their current models. So today we're going to discuss about kind of a few things around synthetic data. So why synthetic data in the first place? Like, why do we care about synthetic data? A bit about the beyond web way of generating synthetic data and kind of how does that work? And that's something that we've done internally at Datology. It's our research. And then how do we put this into production, and how do we kind of ship to our customers the pipelines that generate kind of trillions and trillions of synthetic token at scale, and the engineering lessons that we learn around the way for doing these things. So why synthetic data in the first place? With the scaling laws, you need exponentially more data, exponentially more compute to get better and better models, right? So at some point, there's this idea that you run out of internet data, and we call that the data wall. So the idea behind synthetic data is that you can generate a lot more data in the first place so that overall you can get to the volumes of data needed to train better and better models. This has a bunch of problems in general. One of the most common one is the mode collapse one, where you kind of learn the modes of the distribution and not the tails. The way that we do this, and we call this kind of beyond web, is by rephrasing documents or restructuring them in various places. So how does this work in the first place, and why does this matter? So the idea behind rephrasing is that you kind of take existing data points, and then using some sort of prompts that you come up with, you can rephrase your documents in various ways that kind of increases your data diversity over the corpus, right? So what we've seen through our experiments, and kind of we have this blog post that kind of goes deeper into this. We've taken our beyond web data set, which is about half synthetic, half web tokens. We compared it across a number of data sets: Nemotron Synth, Cosmopedia, QA Wrap, and Red Pajama. And what we've seen is kind of the things that I was talking at the beginning around kind of better and faster models, right? So what we see here, and we have plotted on the x-axis the number of billion of parameters for the models, and then on the y-axis the overall accuracy, that we can train just better models using this synthetic data paradigm, right? So also another interesting result is that, for example, our 3B models kind of match the performance of the 8B models on the other data sets that we've compared ourselves against. Same one in terms of speed up. So here we plot on the x-axis tokens, on the y-axis average accuracy, and we see that we basically train models to the same performance in between 2.7 to 7.7 times faster. So much, much faster training if you generate synthetic data the right way. So how do you do this? So fundamentally, this is straightforward, you would think. You start from a target data set, which is kind of the input data to this pipeline. There's actually quite a lot of work in identifying what are the right documents to rephrase in the first place. You have a bunch of GPUs and a bunch of models. You use your GPUs and you get synthetic data. And we can do this for rephrasing. We can do this for recapturing images, et cetera. in practice, this becomes extremely hard at scale. Like everything at scale kind of gets much, much harder. Turns out that being able to maximize the utilization of your GPUs and have reliable generation over trillions and trillions of tokens becomes extremely hard. And this is what we're going to talk about today. So where did we start? So this is very much like everything at Datalogy starts from the research side. So we're an engineering and kind of research company. A lot of things start from the research side. So it very much started not being integrated in the core product. It started where there was kind of a dual track for curation where you would generate first synthetic data in our Slurm cluster and then move it to the Kubernetes-based cluster. And in generals, it was fairly slow and error-prone, right? So our stack usually lives inside Kubernetes. This is what we normally deploy to our customers. We keep our data in some sort of object storage. We use Flight, which is our kind of workflow orchestrator. It's an open source project. And then we have a bunch of Spark jobs that kind of we implement our curation algorithms into. And then on the research side, we had this Slurm cluster that this is where we would use the synthetic data generation. And then we would be able to have various scripts to generate data there. This was extremely slow. We had a bunch of reliability problems, of course, in this way, and then this was not part of the core product. So what do we do now? Now we basically have put everything into one big pipeline that we can easily ship to everybody. It can run in various cloud providers, or we're starting with AWS. And now we basically have the capability by leveraging Kubernetes and Ray to be able to run inference at scale in this way. So we use the same orchestrator. We've written our own scheduler that is able to schedule both kind of Spark and Ray jobs and any sort of vanilla Kubernetes jobs in the future. And we can orchestrate over the resources that we have available, right? So we can run some Spark jobs. We can identify the data that we need to rephrase, and then we feed them into the rephrasing jobs. All of this being orchestrated by kind of Flight, by our scheduler, and by Ray and KubeRay, and of course vLLM. Awesome. So where are we now? Now it's in the core product. It's cohesive. It works well. It works well at scale, and we can kind of schedule across various clusters that sit in various cloud providers. It's a lot more reliable, and first and foremost, it scales. And I'll let Fan talk about the engineering challenges that got us into the place we're at today.
As you know, Rome is not built in one day. Although like these two slides, just 1 second, it takes us to tackle some key challenges to reach there. So first of all, the first challenge we hit is at this trillion token scale. So for the pre-training data scale, we crawl the whole internet. So if you don't want to crawl the internet, you can use some public data set. And if you check the Hugging Face data set, FineWeb, DCLM, Nemotron, all together, you're going to have more than 30 billion trillion tokens. And if you want to do the data curation for multimodal data, the data comp XL, it has like 12 billion image taxpayer. So in that sense, one job, you will have your data set footprint up to more than 600 terabytes. And our storage already reached at petabyte scale like earlier this year. So what does this mean? At this scale, it means we have millions of data partitions stored in the cloud. And when we try to run the job, we will have a lot of S3 requests throttling. And the first problem we hit is this read-job metadata bottleneck, which caused our GPU being long idle. So what happened behind the scene? Let's say we have millions of partitions stored in the S3 server. And the read-head will fetch this metadata fetching process for each file partition. Let's say it's 400 milliseconds per request. And we're going to fetch like millions of requests. Sometimes we get some throttle. And we have like a retry and backoff slow us down to average 1 second per request. In this process, once read-head has its metadata, it will write to its own metadata storage. As you know, it's a GCS. It has some files, how to partition its file partitions to like smaller blocks, and what's a schema. It relies on this type of information to know how to distribute the workload. Then you have your Ray cluster, which has a lot of the GPU workers already up, but they are waiting for the metadata fetching to finish and distribute the workload. So I want you to do a simple paper math with me. if we have 5 million partitions and we file 5 million head requests for 100 and 400 milliseconds per head, per head request, in total for single-threaded metadata fetching, it will take 7 days to finish. And if we say like a 5% request gonna get throttled, it adds another 2 to 4 days, and in total it will be 9 to 11 days. And all of these 9-11 days, your GPU worker doesn't do anything. It's just idle waiting for the distribution happening. And another GCS metadata, we have to manage the growing the metadata storage while you deal with like a scaled data set. So this is no idea. And how do you solve this problem? So we back to our first principle and ask ourselves, what's the minimum metadata we need to distribute the workload? So it turns out we can do this way. We still have a lot of partitions stored in the S3, and Rehat just lists all of the file partitions, and then write to the metadata as only the file name and the size. And each worker can get like a equal loaded as total file length, total file size divided by number of workers. So this is very like manageable. If we look back to our simple paper math again, for the 5 million partitions, we only need 5,000 requests. And for like 100, 400 milliseconds per list request, it only takes us 2 hours, even for this single-threaded metadata fetching. And only a few thousand, we may not get throttled at all. So in this way, like 2 hours in total for the metadata fetching and the GCS metadata, because we only store file name and the size, we shrink the metadata storage from the 12 gigabytes to 0.5 gigabytes. So if you see this design, we kind of shrink the metadata fetching time from 11 days to 2 hours. And then my coworker asked me, can we squeeze to 1 second? It turns out also doable, and it can do in multiple approaches. One like Rehat can fetch the list of files and distribute immediately. And while GPU workers are streaming the batches, doing the inference and write out, Rehat can fetch the next batch. So this is called like a prefetch and a pipeline parallelism. Another way, all of this metadata can be stored from the upstream metadata, and we can just cache it and reuse here and distribute directly. So both ways can work, and you may have another smart idea can make it faster. But in these different approaches, we make the GPU worker always generating tokens while it's up. So let's recap. We talked about the challenge is this long GPU idle time for this metadata bottleneck. And our solution is like offload this data partition work to the upstream Spark jobs. And our RAID job only handle this lightweight file level distribution. And we can also cache the metadata and prefetch asynchronously to make the GPU always hot. And in this way, we reduce the GPU idle time by 99%, or even you can say almost 100%. So at this point, we can make our job handle a trillion token scale. And our job started to become very long running. So another challenge we hit is this long running inference job that can run few days. And right now, our synthetic data, our coworker is currently running, and it's running for a few weeks. And GPU nodes can fail or replaced by our GPU providers. A lot of talks, they already mentioned how instability the GPU infra is, and we have to deal with that. And this is a real story. Our coworker, our researcher complained to us, his job failed at last 1%, and it takes like a few days to reach here, and then he has to reprocess everything, and he's worried it's gonna delay the delivery. So this is not ideal. But because the first solution we built, we kind of built up this nice one-to-one partition mapping for the RAID job. So what I meant is like for Spark job, like you can see we have partition 0, partition 1, partition 2 written out, and RAID job for all of our map style, like transformation, for example, rephrasing, scoring, and filtering, even can be do like exactly one-to-one mapping, and partition 0 can read one partition and write out one partition. So this nice one-to-one mapping enable us to do this traceability across our data flow. And if they fail, we know where to resume. It also help us to reduce the repartition work and the shuffling work. It actually largely reduce our latency for our end-to-end data curation pipeline. So I want to show some animation here. We still have this control cluster and a compute cluster. And now we are running a Spark job, writing like 3 partitions here. And we have this asset tracker, which Bogdan already mentioned, saying this job finished, this asset is complete, then kick off the next job. And the next job is a ray job. It consumes like this one-to-one mapping partition 0 right to the inferenced partition 0, and partition 2 right to the inferenced partition 2. And then we have this checkpoint mechanism say, OK, this GPU node failed at writing partition 1. We have this checkpoint saying this job failed, and the asset tracker say, let's retry. And this retry rejob will pick up the progress, only process the last 1% of failed progress. So in this way, we can turn the multi-day job failure to recover retries. Just to recap, we talk about this GPU node failure can disrupt our long-running inference jobs. And our solution is to have this resumable execution and build up this idempotency between the storage and read job, so to ensure us to be able to safely retry and no side effect like duplicates and partial write-outs. And everything is tracked, so we have seamless recovery. So the researcher doesn't need to monitor the job progress, and everything can be relaunched and on any available GPU node. So to this point, we can shorten the GPU idle time and make our job resumable for this GPU node failure. But as everyone talked about in this conference, we run out of the compute, right? Everyone knows we need more compute. We need to cry to Jensen to get more compute. So our trillion token scale already pushed our GPU capacity limit. So we really need to orchestrate our trillion token workloads across different providers or clouds. But like scheduling heterogeneous job can lead to many edge cases, many fragmentation, many idle GPUs. So you may also waste your cost money on the GPUs. So some edge case I want to show you here. Let's say we have a CPU pool and a GPU pool. And timestamp 1, we have a CPU running here, and it can feed into the CPU pool, start running. Timestamp 2, we have a GPU job, which has read placed in the CPU pool and the read worker placed in the GPU pool, and start running as well. And the timestamp 3, we have this CPU job again, which takes the whole capacity of the CPU pool. And at this point, another GPU job comes, and it has to wait because the read head cannot feed into the CPU pool, even though you can see the GPU pool has some space to feed the read worker. So in this case, we have some amount of wasted GPU, or wasted, if you have on demand, it's like wasted GPU quota as well. So our read GPU jobs start to sit in the queue, and we have waste GPU. You're going to waste money here. And another case I want to show you is same as like a timestamp 1, we have CPU, timestamp 2, we have GPU. And the only difference is timestamp 3, we have a very hungry CPU job, can handle like a terabyte scale of data set, and cannot fit in the CPU pool. So this single CPU job gonna block all of the GPU job later on. Even this timestamp 4, this job GPU job can fit in both CPU pool and GPU pool. And in this way, we not only waste some GPU, we also waste some CPU, and we don't want to block our GPU workloads. So how do we want to solve this problem? It turns out like we can group the head to its own pool and have this drop queue segmentation. And I'm going to show you the animation here. We still have our control cluster and the compute cluster here, and everyone is based on Kubernetes. And we build up this job queue concept. We have like a different job type. For example, Spark job goes to its Spark job queue, and Ray can go to its own GPU job queue. And then we have our in-house job scheduler. So workflow orchestrator kick off the job. Job scheduler will check the job where it should go to. So first of all, what we showed before, timestamp 1 is a CPU job. It can fit into the Spark pool and fit in the queue. It starts running. And then we have our read head placed separately in the head pool. And it's owned by this job queue here. And timestamp 2 is a GPU job. It can run as well because it doesn't share the same pool as a Spark or CPU pool. And then timestamp 3, we have another CPU job here. And timestamp 4, we have a GPU here as well. So you may say like on-demand GPUs, they are kind of cheaper. They are kind of L40s, and you get from demand. And you may have some reserve cluster, and you want to speed up your job. Then our scheduler config can route the read job to the like a super compute cluster. So this arrow here can have another alternative to route to this our H100 cluster. We can have timestamp 2, timestamp 4, these two jobs running here and later here. So our schedule config is a very simple config. User can define as launch time, and it can define where the job should go to, and what's the ordering policy for each job queue. Can be force in, force out, priority based, or preemption enabled, and fairness aware. So it can also route the job to different node pool. Just to recap what we talk about, so we talk about how to orchestrate trillion token scale workloads across GPU providers and clouds. And our solution is we build our in-house scheduler with one single config to schedule our job anywhere. And the job is portable across the cloud, clusters, and providers. And we still have the previous benefits. We have centralized metadata and the lineage tracking to ensure we have like a unified visibility and traceability across the clouds. So to here, we already kind of close to the linear scaling law as Bogdan presented. Now, another problem we want to solve is we want to push the slope a little bit higher. So we do inference optimization. So first of all, we use vLLM as our inference backend, and we love vLLM. A lot of times, the default is very optimized, but sometimes it's not optimized if you have different setup. For example, Quinn is heavily optimized with vLLM, whereas we found another great rephrase model called OMO is not optimized at all. And the throughput, it turns out like a quarter or like less than 20% of a Quinn model. Even the model size is the same. And you know, like vLLM, a lot of benchmark vLLM to the parameters is done by H100 or A100. When we don't have enough H100 nodes, when we adopt this parameter to L40, it turns out it's not optimal at all. And the data accuracy, like token length and the batch size also change these settings. And we also don't want over-engineering because vLLM release very quickly, and then today's parameter is going to be outdated tomorrow. So how do we fast discover the optimal vLLM parameters? This is our key takeaway, and we like to share our share after the talk. What do you think? So we focus and identify the key levels of the inference speed up. The first one is the batch size. And the batch size can be the data batch size and also the continual batching inside of vLLM. Another thing we found very powerful is this specular decoding, which can use a draft model to speed up the things. Sometimes we don't have a draft model in hand, and we found ngram is actually quite powerful. Another caveat I want to share is like I tried the ngram default parameters with OMO. It turns out slow down the throughput a little bit. And we have to sweep these two parameters and to make it best perform. And as an outcome, we have 40% throughput gain compared against vLLM defaults on OMO model and the L40s. Just to recap what we talked so far. We talked about, first of all, how do we scale at trillion token? And secondly, we talk about how do we auto-recovery for any GPU failures for long-running jobs. And thirdly, we talk about how do we empower us, unblock us with all of the GPU providers by building our own scheduler. And lastly, we talk about how do we rapidly search our optimal vLLM parameters without over-engineering. Now I'm going to let Bogdan talk about the outcome and impact.
Awesome, thanks, Fan. So what are the outcomes of this, right? We started, I think, end of last year, generating about 30 billion tokens. That was very much in our kind of research setting. At the beginning of this year, in like late spring, we generated about 1 trillion tokens for one of our customers. And right now, we're processing, as we speak, a fairly large data set of about 7 trillion tokens all of this being just the synthetic data part. So using this setup, you can get to fairly large-scale synthetic runs. Probably 7 trillion tokens is probably one of the largest synthetic data runs for text in the world. We're continuing to push the boundaries of this. We're doing a bunch of active research in this domain. I think if you look in Datology's research team, probably everybody works on some sort of synthetic data generation right now. And we're expanding this across various domains, web, multilingual, math and code, multimodal as well as domain-specific data sets, for example, for legal data. So this approach is fairly generalizable. You can push it in various ways, and we've done it successfully at fairly large scale, while we empower our researchers to continue to iterate on this stuff as well. So in terms of reflections and future directions, there's a couple of things here. There's a packing problem that we want to solve, which is how do we kind of route the synthetic data and the GPU jobs to the right clusters that are kind of the least utilized? How can we kind of collocate CPU and GPU jobs on the same kind of hardware? So in the case of H100s, we get hundreds of vCores per box, and our training jobs and inference jobs don't use all of them. Maybe they use 20–30%. How can we leverage those CPUs for other things? And how can we improve data locality overall, right? Especially if you're running in any sort of other cloud provider, then you need to move this data over the network in various ways. How can we reduce that? Another thing is about smart scheduling, right? Like if we know exactly how much time each job takes, then we can properly allocate resources in the most optimum fashion possible, right? So if we know that ingestion is going to take this much time, and then synthetic data and this model is going to take this much time, then we can kind of figure out exactly what job goes where and how much time is it going to take, and then we can prepare dependencies and we can overlap compute as well. So finally, we're hiring across of roles, data infrastructure, training and inference infrastructure, how we package and kind of deploy our product. Let us know if you're interested. And then I want to thank my team. A chunk of them are here, so if you have questions, they're going to be here in the audience. Thank you so much. This is a huge team effort. This is kind of the people on the slide are just a chunk of the people that work on some of this work. And thank you for the larger Datology team. And I think that's it. Thanks, everybody.
Looks like we have time.
We have 2 more minutes for questions.
Yeah. Hello, testing.
Thank you so much. Great talk, Bogdan and Fan, and great to see Josh Wills on the slide. So I think the engineering is great. I have a slightly kind of unrelated question. So synthetic data, right? So you generate trillions of tokens of AI slop, which is then used to train various frontier models. How realistic is this that the quality is high? We didn't talk much about quality.
Right,
like, are we going to be drowning in the sea of slop, and every subsequent model is going to be worse and worse?
I think this is where a lot of our rephrasing work goes into, right? Like, how do you rephrase them in a way that you're not generating slop, right? I think we're also starting to see that there's opportunities to be able to filter this after you generate it, right? I think we're seeing some amount of work around how kind of true this data is and from a content perspective. So there's opportunities to use LLM as a judge and be able to tell, hey, this is actually factually not correct, or something is wrong with this. So there's opportunities to kind of be able to filter this data afterwards, but a lot of work goes into ensuring diversity and like only rephrasing the data points that are worth rephrasing, that are already high quality. So if you're starting with high quality data, then at least you have a chance of getting high quality outputs as well. And all of this stuff is highly experimental. So we've been running tens of thousands of oblations over this stuff, figuring out what works and what doesn't.
Hi, thanks for the talk. I have a quick question. How do you coordinate the Spark workload and I guess the rest of the workload? Do you have something that manages the compute graph or something like that?
So we use this scheduler that Fan was talking about, where we know what job comes kind of next in that perspective, and then we can, the scheduler knows how much capacity do we have at a given point in time, and if we need to auto-scale and increase the capacity of this cluster, we can do that as well. So that scheduler is the key component that lets us kind of schedule diverse workloads.
Great. I think that's all we have time for. Thank you so much for that great talk, Bogdan and Fan.
Awesome.
And
Thanks,
thank
everybody.
you to everybody for attending. See you tomorrow.